Hello guys and welcome to a new video. I'm Max Webful and today we're gonna try solving a really interesting question related to trigonometric functions, Taylor series and a little bit more. So if I ask you, would you be able to find the radius of a circle just knowing the chord and the subtended arc length? I wasn't at first, of course, but after trying a few things, I got really interesting results that I want to share with you today. So stay tuned. First of all, we have to find a relation between the radius and any of these two things. So, I don't know, let's just start doing something like this. I imagine what would happen if I drew this line here representing the radius. And yeah, that doesn't really work, but what if, I don't know, maybe I drew another line in here, like a random line, also representing the radius. Yeah, that doesn't quite work either. But wait, what if we draw a rectangle triangle? Okay, so this is 90 degrees. Okay, so because we know this, we know the length of the chord. If we divide it in half, here in half, this will be also the radius. But this is gonna be a 90 degrees angle. So we got a rectangle triangle in here. Okay, so maybe let's call this theta. Okay, so then, because this is dividing half of the circle, this will be s/2, and this also be s/2. This also be c/2 and c/2. Okay, so now we have a trigonometric relation, right? Because sine of theta equals opposite over hypotenuse. So opposite c/2 over r, which is the hypotenuse. And simplifying, we got c/2r. Okay, and then maybe, I don't know, try solving for r, because that's what we want to calculate. So we solve for r, this go here and this go here, so it's c/2 sine of theta. Okay, so we got one expression for it. Let's see what else we can do. Wait a minute, I see something here. I remember that if I have an angle theta and I want to calculate what is the length of the arc, I can just use this formula, which is the arc length is equal to theta in radians times r. And this makes sense, right? Because if I want to calculate the arc length of the whole circle, what will it be? It will be, what is 360 degrees? Is 2 pi, right? So 2 pi times r equals arc length. And this is exactly the perimeter of the circle. So if I wanted to calculate, for example, just half of it, what will it be? It will be just pi, right? Because if the whole circle is 2 pi, half of it is just pi. So it will be pi r equals this thing. Wait, I forgot the ht. So it makes sense to say that s/2 equals theta times r, right? And we don't know, we don't know yet theta, neither r, but we've got kind of two equations here. So let's try solving for r in this one. R equals, let's get this down here, s/2 theta. So we now have two expressions that relate the radius and theta. So let's set them equal. We go right over here and we write radius equals c over 2 sine of theta, and also radius equals less over 2 theta. And this is a system of two equations consisting of two variables. But yeah, it's pretty easy to see that we can set them equal. So c over 2 sine theta equals s over 2 theta. And we make cross products, and it gets like this. 2 sin theta equals 2 sine of theta times s. Well, we got two 2's, so we cancel them out, and we are left with theta, also solving for theta, equals sine of theta times s over c. So, do you know what this is? This is a transcendental equation. And why is it called like that? Because it doesn't have any standard solutions. I mean, you cannot solve for theta. It looks like this is solved for theta, but we also have theta here. So it's impossible to solve for the variable. And what can we do in these cases? Let's figure it out. Do you recall hearing sometime the term Taylor series? Well, if not, I'm gonna introduce them for you. So if we have a transcendental function like e to the x or natural logarithm of x, something that cannot be written as a polynomial like this, x squared plus x third, etc. Or more specifically in this example, sine of x, which goes like, sorry for the focus, goes like this. There's actually a Taylor series that can approximate with algebraic notation a transcendental function. For the Taylor series of sine of x, this is equal to x minus, what's it? I think x third to the 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and it goes on and on, right? So this is a really useful. Oh, if you want to know how they look on here, for the first term it's just like this, right? Just the x. For the second term it goes like this. For the third term it goes like this, and so on. So we are basically constructing the function sine of x with a polynomial expression. So we can use this to our advantage in here. So let's rewrite sine of theta in this form. We write theta equals s over c times, if you notice, for small approximation we can use just to this term. So let's use just this term. Is x, oh sorry, theta, because that's our variable in this case, theta minus theta to the third over 3 factorial, and that's it. We notice that we have in common theta in all our terms, so we can divide over theta. We are left with 1 equals s over c times 1 minus theta squared over 3 factorial, which is actually equal to 6. So let's write down. Then we can solve for theta also. So I'm gonna do that. C over s equals 1 minus theta square over 6. This is 6, and then we move this to the other side, and it's theta square over 6 equals 1 minus c over s, and then we cross multiply. Theta square equals 6 times 1 minus c over s, and we get the square root. Theta equals square root of 6 times 1 minus c over s, and it's the positive because it wouldn't make sense to have a negative theta, so we just get this thing. And then we actually got an expression of theta knowing these two things, the chord and the segment. So now that we have this thing, we can substitute on the first formula, which is, for example, this equals s over 2 theta, and which theta being equal to this, we write r equals s over 2 times square root of 6 times 1 minus c over s. And that's it. We've solved for r. I hope you guys enjoyed it, and hope I see you in another video. Ciao.